All right, good morning, stat students. We're starting Chapter 7 today, and Chapter 7 is going to cover the normal probability distribution. Now, the normal probability distribution deals with the normal curve, so we're going to be looking at a lot of things related to the empirical formula that we've referenced, I believe, back in Chapter 3, and mean and standard deviation, what that, how to use that in situations applied to probability and percentages and proportions of a population. So the normal probability distribution, and in Chapter 7.1, specifically the properties of the normal distribution. And we're going to look at these objectives. We're going to use the uniform probability distribution. Now, uniform probability distribution is not normal. Okay, uniform probability means every possible outcome has the same probability. That's not a normal curve, but anyway, we'll talk about what that is. Graph a normal curve, state the properties of the normal curve, and explain the role of area in the normal density function. Okay, so let's move on. You will not need a graphing calculator today, but later on in this section there will be a lot of graphing calculator activities that we'll look at. So the uniform probability distribution, here's an example of it. Suppose that the UPS is supposed to deliver a package to your front door and the arrival time is somewhere between 10 a.m. and 11 a.m. So that's a 60-minute window, right? Let the random variable x represent the time from 10 a.m. When the delivery is supposed to take place. The delivery could be at 10, which would mean x is 0, or at 11, which means x is 60, with every 1 minute interval of time between x equals 0 and 60 equally likely. That is to say, your package is just as equally likely to arrive between 10:15 and 10:16 as it is to arrive between 10:40 and 10:41. The random variable x can be any value in the interval from 0 to 60. That is, x is 0 is less than or equal to x, which is less than or equal to 60. Because any two intervals of equal length between 0 and 60 inclusive are equally likely, the random variable x is said to follow a uniform probability distribution. Okay, so this is just an illustration of what a uniform probability distribution is. A package is as likely to arrive at x equals 1, which would be 10:01, or between 10 and 10:01, and x equals 20, which would be between 10:20 and 10:21. So that's the intervals of time between 10 a.m. and 11 a.m. that we're concerned with. So if we were to graph this probability distribution, uniform probability distribution, we're going to see something that's pretty neat. We're going to see a probability density function. It's an equation used to compute probabilities of continuous random variables. It must satisfy the following two properties. So the total area under the graph of the equation over all possible values of the random variable must equal 1. Now, this isn't new, right? This concept has been with us a lot of things. Think out loud or think to yourself, what are some things related to statistics that must equal 1, right? So what we're talking about here is a probability distribution, and the sum of all of the probabilities has to equal 1, right? So we're talking about the area under the curve has to equal 1, so we're going to be using areas to represent probabilities. The height of the graph of the equation must be greater than or equal to 0 for all possible values of the random variable. Okay, so greater than or equal to 0, again, is that a new concept? Don't all probabilities have to be greater than or equal to 0? Right, we can't have any negative values on our graphs because probabilities must take on non-negative values greater than or equal to 0. So let's look at an example that we just illustrated with the Postal Service. The graph below shows the properties for the time example. Notice that the area of the rectangle is 1, and the graph is greater than or equal to 0 for all values between x equals 0 and 60. Because the area of a rectangle is height times width, The width of the rectangle is 60 minutes. The height must be 1/60th, and it is 1/60th because the probability that it'll arrive in any of those minutes through that hour is 1 out of 60. So 1 minute out of 60, the probability of each time slot is there. So this is what a uniform density function looks like. It's always going to be a rectangle. It's not going to be a curve like our normal curves or any curve that was skewed right or left for that matter. But that's what it is going to look like. All right, so the values of the random variable x less than 0 or greater than 60 are impossible. Thus, the function values must be 0 for x is less than 0 or greater than 60. That just means we're not interested in times before 10 a.m. and we're not interested in times after 11 a.m. and so there's no probabilities outside of those time slots that are meaningful for us. Okay, so the area under the graph of the density function over an interval is going to represent the probability of observing a value of the random variable in that interval. Now this just makes sense, right? Because if we talk about the probability of it arriving, let's say if we cut this into half, 30 minutes, right? The probability of it arriving over here in the first 30 minutes is 30 out of 60. The probability of it arriving over here in the second 30 minutes is 30 out of 60. Both of those are equal to 1/2, and that is the area of the curve as well. Area under the curve, and I say curve because this. I know it's a flat line, but it's a function, it's a curve, it's a line there that we're looking at. So that's going to continue to be true whether it's a uniform distribution or a curved distribution, a normal distribution that we're going to look at in just a few minutes. So the area under the curve represents the probability. So if we looked at the area or probability that it was going to arrive between 10:15 and 10:30, okay, that's 15 minutes out of 60, right? And 15 out of 60 is 1/4. Well, that's also the area of the curve because the width of this rectangle is 15. The height is 1 out of 60, and 15 times 1/60th is 15 out of 60. So we can use area to represent probability. The area and the probability are going to be the same. All right, so now let's look at the graph of a normal curve. And we're going to apply these same principles that we just looked at to a normal curve. But the relative frequency histograms that are symmetrical and bell-shaped are said to have the shape of a normal curve. Now, the normal curve is this curve that we could draw around it. It's also called the bell-shaped curve. That is the normal curve that fits this thing. And just like the uniform distribution, it has certain properties that we're going to be interested in. And let's look at those. If a continuous random variable is normally distributed or has a normal probability distribution, then a relative frequency histogram of the random variable has a shape of a normal curve or bell shape. So our histogram is normal. This is a histogram in blue, and it follows kind of roughly the shape of a bell-shaped symmetric normal curve. Now, this is kind of showing us some stuff that this may be a new definition for you. An inflection point is where a graph changes shapes, so to speak. And here's what we mean by shapes. This graph goes from up here. Let me switch my tool. Up here, it clearly has a downward shape, right? It's opening downward. But if we just looked at this part of the curve, it's cupping up, right? And where those upward cup and downward cup meets is called the inflection point. So an inflection point of a graph is where it changes from concave down, like this is concave down, to concave up. The shape of the graph there is concave up. All right, cup, concave up. All right, if it'll hold water, it's concave up. And of course, it won't hold water, but the shape would be, part of something that holds water. So this is concave up, and this is concave down. And the point where the concavity changes is called the inflection point. All right, so that's something that you look at a lot in calculus and some other maths that maybe you have had or maybe you haven't had. But the point of inflection always occurs. Let's look at these things down here at the mean minus 1 standard deviation and the mean plus 1 standard deviation. That's where the point of inflection always occurs. So the shape of the graph changes there. So when you're getting ready to label graphs, identify the points of inflection. The points of inflection will always be exactly 1 standard deviation above and 1 standard deviation below the mean. All right, let's put that, just to make sure you understand. Let's put that into concrete terms. If this is IQ, average is 100, standard deviation is 15. This is 115. This is 85. So at 85 on our horizontal axis, that's where the inflection point is going to take place or change. The graph changes shapes at that point. All right, so that's an important property of the standard normal, symmetrical, normal distribution, normal curve, right? Bell-shaped curve, all those different names for the same thing. All right, so these are just some examples of graphs of normal curves. If we look at the ones up top here, we've got this one has clearly we can see that the mean is at 0 and the inflection points occur at 1 and -1, so that means the standard deviation is 1. Okay, this other curve also has a standard deviation, looks like it has a standard deviation of 1 because at the place where the graph changes shapes there is at 4, and the mean, the middle point, the peak, is at 3, and so it has a mean of 3 and a standard deviation of 1. Now, the two graphs down at the bottom do not have the same standard deviation. Now, if you'll notice, the standard deviation is what's going to kind of determine the shape of the graph, the height of the graph, the peaks. That's the smaller your standard deviation is, the taller your graph is going to be. So let's look at these two graphs in comparison down here on the bottom, and you can see that the pink graph has a mean of 0, and it looks like it changes shapes there. We'll take that, so that's at 1. So the mean is 0 and the standard deviation is 1. But if we're talking about the blue graph, now what they do have in common is that the blue graph still has a mean of 0, but it looks like this is not, if we're looking at the blue graph, right, this thing right there, the graph doesn't change concavity at that point. The graph changes concavity at this point. And so our standard deviation is 2, okay, and that makes the graph spread out and more lazy, right? Wouldn't we expect that? What does standard deviation mean? What does standard deviation mean? It means the average distance that values are away from the mean. So if the standard deviation is higher, then our data is going to be pulled out farther from the mean, right? So we're going to have more values out here farther away from the mean if the standard deviation is larger. So just kind of make a mental note, tall, skinny graphs, normal curves have a smaller standard deviation than, short, wide ones. Okay, so just kind of some facts that'll help you. Now, here's the properties of the normal curve. Properties of the normal curve, and we've talked about all these up to this point, but let's look at them. It's symmetric about the mean, right? It has a symmetrical shape, and that's true of our histograms of graphs of distributions are the same. They'll have symmetry around the mean. And because the mean is equal to the median is equal to the mode, the curve has a single peak, and the highest point occurs at x equals mu, which is our mean. Right? It has a single peak. Okay, it has inflection points at 1 standard deviation below the mean and 1 standard deviation above the mean, right? So mu minus sigma and mu plus sigma, that's where the inflection points or the graph kind of takes its change in shape. Now this is always going to be true as well. The area under the curve is always 1. If it's a normal density curve, it has to have an area of 1 underneath the curve. So we'll see a little bit more about that in just a second. The area under the curve to the right of mu equals the area under the curve to the left of mu, which is equal to 1/2. And that's really just a restatement of property 1, which is symmetric about its mean. So if the area is 1, right, and it's symmetric, then it has to have an area of 1/2 on either side of the mean. Okay, and as x increases without bound, that means as the value of our variable. Let's give some meaning to this. As IQ increases, right? As a person's IQ or IQ measurement gets higher and higher, the graph approaches but never reaches the horizontal axis. So as IQ gets higher and higher, the probability of a person having that IQ is less and less. All right, but we can't rule out the possibility that there might have been or will be a person that has an IQ of 300. So the probability is minuscule. It's infinitesimal. It's very, 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 very small. But we cannot say that the probability ever actually gets to 0. All right, and then number 7 was our old friend, the empirical rule. These facts are very important, and I am going to put the empirical rule data give you a slide of that in the Chapter 7 resources page. But 68% of the area is between 1 standard deviation below and 1 standard deviation above. So we could say 68% of the area of the curve is within 1 standard deviation of the mean. 95% of the area is within 2 standard deviations of the mean. And 99.7% of the area is between 3 standard deviations of the mean. So 3 standard deviations above, 3 standard deviations below. So the empirical rule is going to play an important role in Chapter 7. And here's a graph of that just shows that 68%, and this gives you nice symmetry. So we got 34% here and 34% there. 13.5 and 13.5 adds to 68 to give us the 95 between those two values, and then so on and so forth. So let's put numbers on this again. I like to put concrete things in here. IQ, if this was IQ, standard deviation is 15, so this is 115, this is 130, this is 145, and this would be 85, 70, 55. Right, so 34% of the population has an IQ between 100 and 115. So that's how we're going to use this this graph, and we've done this before, so it's not going to be new. But we're going to put a little bit more meaning to it, or a little bit more technical language with it as well. So explain the role of area in the normal density function. So this is where we're going with this chapter. This objective is really setting us up for what we're going to be looking at next. So let's look at an example. The data on the next slide represent the heights in inches of random sample of 50 two-year-old males. Two-year-old males, I love that. Two-year-old boys, babies. Draw a histogram of the data using a lower class limit of the first class equals 31.5, class width of 1. All right, so if we were actually going to organize this data, we're not. We're going to look at the graph that they've given us. Do you think that the variable height of two-year-old males is going to be normally distributed? Now, wouldn't we think that we've got 50? That's a pretty large number. Something that's natural, 50 of something that's natural, like height, shoe size, weight, those types of things in a population are going to approach normality. So do I think the variable height of a 2-year-old male is normally distributed? I would think that we could expect it to be normally distributed. So let's look at the values. This is the values, and if we were going to do this, we would create our tally. Just want to remind you how to do this. The first class, I think they said, was 31.5, or was it 30.5? I think it's 31.5. So it would be 31.5, class width of 1 is going to take us to 32.4, right? And then 32.5 to 33.4. We would tally up the number of heights in each one of those categories and then draw our histogram, and it looks like that. So you can see that we have something that looks fairly normally distributed. You know, we have a lot of symmetry going on here. These two rectangles are about the same size, or exactly the same size as our the next two rectangles are about exactly the same size. There's a little disparity between these two, but it's not much. These two are about the same size, and then we've got one peak, which is important. So, you know, what we've got here is something that is normal, or certainly it's approaching normal. If we had 50 more males in our sample, we would expect the two rectangles that are a little bit off to start getting closer to each other. Okay, it's closer in size to each other. Now, if we take this and draw a normal density curve over the histogram, and they're asking us to see how does the area of the rectangle corresponding to a height between 34.5 and 35.5 inches relate to the area under the curve between those two heights. So take the area of the rectangle and see how it compares to the area under the curve. So how does the area of this rectangle between 34.5, how does that area compare to the area under the curve, which is going to be all of this area, right? So we're talking about area there. Now, you guys don't have the calculus to calculate the exact area of that curve, area under a curve, because this is shaped like this. I mean, it's roughly the shape of a trapezoid, so you could use a trapezoidal height to approximate it. But what they want you to do at this point is to see that, you know, this little area right here that is above the curve is, you know, it's a little bigger, but it's roughly the same as that area, right? So if we took this area out here and we shaved it off and put it inside over here, where the area under the curve and the area of the rectangle are roughly equal. Okay, and there's shading to show what we're talking about. So if the curve here would, if we shave this little rectangle off right here and put it there, we would see that the area under the curve is really, really close to the same as the area of that rectangle. Okay. What is the area under that curve? Incidentally, it looks like it's at 20%. So the area underneath this curve has a width of 1, a height of that's 0.2. And because this is a probability distribution, we know that all the areas of these rectangles are going to add up to be 1, right? And that means that the area underneath the curve that's graphed here is also 1, or approaching, getting close to 1 in that interval. All right, so let's move on. The area under a normal curve. So let's suppose that a random variable x, what could this random variable x be? It could be heights, like we just looked at. It could be IQ, like we've been talking about. Suppose that the random variable is normally distributed with a mean of mu and a standard deviation of sigma. the area under the normal curve for any interval of values of the random variable x represents one of two things. There's two ways we can interpret it, okay? So the area that's under that curve represents either the proportion of the population with the characteristic described by the interval of values, okay? So if we go back to our standard normal curve just a moment ago, and we look at that as a proportion of, we said IQ is 100 and one standard deviation is 115. 34% of the population has an IQ within that interval range between 100 and 115. That's the interpretation that we're looking at there. Now the second interpretation is that the probability that a randomly selected individual from the population will have that characteristic described by the interval of values. Okay, so the area also, it either represents the area either represents the proportion of the population or the probability that a randomly selected individual from the population will have that characteristic described. So if we go back to the same, if we go back to IQ, the probability that a randomly selected person from the population will have an IQ between 100 and 115 is 0.34. Okay, 34% of the population we expect to have that characteristic, right? 34% of the population will have that characteristic, which means the probability that a randomly selected individual from population will have that characteristic is also going to be the same thing. And here's just an example using something other than IQ. The weights of giraffes are approximately normally distributed with a mean of 2,200 pounds. That's a lot of animal. 2,200 pounds and a standard deviation of 200 pounds. Okay, so draw a normal curve with the parameters labeled. We could do that, right? 2,200's in the middle. The inflection point has to take place at 200 above that, so we'd have inflection points at 2,400 and 2,000. Right? Shade the area under the normal curve to the left of 2,100 pounds. All right. So we would shade the area to the left of 2,100 pounds. Suppose that the area under the normal curve to the left of 2,100 pounds is 0.3085. Provide two interpretations of this result. Now you are going to be asked to do this in some homework problems. Two interpretations of that result. Well, let's look at the graph. There's the graph. Okay? And what they just told us is that the area of this shaded region right here is 0.3085. All right, so the two possible interpretations of that, if we were looking at C and D, and you guys have this PowerPoint, so the two interpretations are that we would expect 30.85 proportion of giraffes whose weight is less than that to be 0.3085, and or 30.85% of the giraffe population has a weight of less than 2,100 pounds. Also, the probability, the second interpretation, is the probability that a randomly selected giraffe weighs less than 2,100 pounds is 0.3085. Okay, so 30.85% of the giraffes would be there. So the probability is 0.3085. There's two ways of stating the same thing. All right, so your homework from this section is here. And we will be moving on to section 7.2 next. I will have that video available to you so you can work on it over the weekend if you would like to, but that homework isn't going to be due until next week. So have a great weekend and make wise choices. Looking forward to seeing you guys again soon.